Okay, everybody, welcome back. What's up, YouTube? That's stupid. I'm going to go ahead and get into week 2, chapter 2. We'll go over Tuesdays. Thursday's lecture I will also upload, but it's going to be a lot shorter. And actually, I will probably make them both part of the same clip. And so yeah, the reason I'm doing that is because I have already gone over part of the lecture on that week, so I'm going to basically skip the part that I've already gone over because it's already uploaded. Okay, so chapter 2, part 1. We have atomic theory and structure. And so we're going to be talking a little bit about Dalton today. Dalton was an old, I believe, Greek philosopher that basically was saying that everything in matter is composed of indivisible atoms, and if you look at my actual slides, you can see how this arrangement of these atoms, like this, when you zoom out, it becomes a gear, and this is the way that these atoms are arranged within that gear to show that it is indeed made of indivisible atoms. And so defining an atom is where we are going to begin. So an atom is a very, very, very small piece of matter, and that is going to change, or is going to remain the same during chemical reactions. So atoms are one of the smallest pieces of matter that we know about, besides what atoms are made of. And so basically you can think of it as a little ball. An element is a specific type of atom. So whatever an element is only ever going to be composed of one single type of atom. It could be many, many atoms. An element, if you had a chunk of bismuth, then that would be many, 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 many atoms. But it is all going to be the exact same type of atom. And so let's go over a couple more definitions. I don't know why this is such bad quality. That sucks. But a compound is something that is going to be two or more different elements, different types of atoms that are chemically combined. And they're going to be in fixed proportions. So you cannot change the amount of proportions. Otherwise, you have a different compound. Chemical reaction is going to involve the rearrangement of those atoms to make a different kind of compound, a different kind of component. And so, when we're talking about the periodic table, we can talk about the atomic symbol first. So, the atomic symbol is going to represent, is one of the squares in the periodic table, and this represents the type of atom that we're talking about. And I'll get into exactly what all of these numbers mean, but for right now, we're just looking at the lettering. So the first letter is always going to be capitalized. The second letter is always going to be lowercase. When it is the first part of a sentence, then we're going to use a capital letter to describe what that is, but if it's part of a sentence later on, and it's not the first word, then it has a lowercase letter. So if you said, I have some mercury, the mercury in that sentence would have a lowercase m at the beginning. And then we can skip to the law of multiple proportions. So when two elements form more than one compound, the masses of the elements in these compounds for a fixed mass of the element are in ratios of small whole numbers. And so I'm not really going to talk about this much, but basically this is how we can look at that. So if we have 1 gram of carbon dioxide or carbon and oxygen forming two different compounds, then the first compound is always going to have this many grams of O2 per 1 gram of carbon. The second compound is only going to contain this much O2 per every 1 gram of carbon. And I believe that this is supposed to be oxygen without a 2 right there, not O2. And so the ratio of oxygen to carbon in both instances is going to be 2 to 1, indicating that the second compound has twice the amount of oxygen in it. And so, yeah, again, I'm not really going to dwell on this too much because it's not super important, so let's continue. So when we're trying to find when we're trying to, but it is important in noting like what we are going to be looking at. So for example, we can use these models, these pictures over here to show what they might look like. And so for CO2, for example, we know that letter E is going to be CO2, and that's because E has two different atoms in different ratios. So there's always going to be, for CO2, one carbon present. There's always going to be two oxygens present. This is always going to be the ratio. And so since none of these other pictures have that ratio to them, then we are going to know exactly which one of these is CO2. Okay, so let's get into the structure of the atom. So on quiz number 2, we talked about the Bohr model. And so this is a very rudimentary explanation of the Bohr model. But I believe his name was Niels Bohr. He came up with this kind of way to show it. Again, this is not exactly what atoms actually look like, but it's more of a planetary model. So what I mean by that is that in the center you have the nucleus, which could be considered like the sun in a planetary model. So nucleus is the center, and then around it you have orbiting particles called electrons, and those are going to be maybe like the planets. And so I could say these are in orbit. So you have electrons circling the center, which is the nucleus. Now, in the nucleus, you have a central core, which consists of positively charged particles, which are called protons, and they contain most of the atom's mass. Protons are about 10,000 times heavier than electrons, so we don't even really consider electrons as part of the equation. Even the heaviest atom is only going to be, I want to say it's like around 250 grams per mole. And so I'm going to use terms like grams per mole because we've already talked about these, but 250 grams per mole, which means that a single electron would be, let's see, this is 10 to the second, so 10 to the negative 3. So a single electron would be 0.002 times smaller. So really, it doesn't add much mass whatsoever. So we don't even consider the electrons when we're taking the mass of an atom. They're very light electrons, and they are negatively charged. And this is to balance the charge of the positively charged nucleus. So it has an overall, the nucleus has an overall positive charge, but it is two different elements, or two different, my mistake, not elements, two different components. And we'll talk about exactly what those components are in just 1 or 2 more slides. But the electrons are going to exist in regions outside of the nucleus. And so if you guys will look at your, kits that I gave everybody, the 3D printed kits, those shapes that you have, the ones that look like this, and like the circle and the butterfly looking one, those are going to be places where electrons can exist. Again, that doesn't look like this ring over here, which is how the place where these electrons can exist are represented, but this is where they actually can exist, is in those shapes. Okay, so for the discovery of the electron, J.J. Thomson, who sounds like the guy who is the editor-in-chief at the place where Spider-Man works, J.J. Thomson used a cathode ray tube for a series of experiments. And so a cathode ray tube is a tube that has electrons that pass through it. It's how they used to make television, I believe. But he concluded that the cathode ray is a beam of negatively charged particles, and that all matter contained these negatively charged particles. He was also able to calculate the mass of an electron in comparison to its its charge. And so, as you can see, the cathode ray tube has a vacuum space in the center where all of the air is pulled out and only electrons are traveling through an air-free space. And then when some kind of magnetically charged or electrically charged item comes close to this tube, that's when the balance between the negative and positive parts of this cathode tube are adjusted, and so you get a deflection of the electron beam. So it starts to go and change direction. And so for the discovery of the electron's charge, however, there is a man named Robert Millikan. And like I said in class, Millikan reminds me of the word milk. Milk can. Oh, God. My cat. Olive. Anyway, Millikan reminds me of milk can. And milk can is exactly what he used to find this. It's not exactly a milk can, but that's how I remember it. And so he was able to find the charge of an electron by observing oil falling in the presence and absence of an electric field. And so he was able to determine that this is the charge of an electron. It's 1.602 times 10 to the negative 19th coulombs. A coulomb is just a unit of charge. And so we won't really get into coulombs until a bit later, but this is indeed what the unit of a charge is. Okay, and so this is what the experiment looked like. There were oil drops that were being atomized in this kind of a milk can. Of course, it's not actually milk, it's a can of oil, but they were being atomized, which means they were just very, very, very small droplets that were falling through this charged metal plate. And so when the charged metal plate was present, then you would be able to get ionization. So you would have a charge attached to the droplets. And so when the charge was flipped on this milk can, when this went up to having a positive or negative charge, whenever the field of charge was flipped from going this way to going this way, some of the oil drops would start to float back up, and that's because they were attracted to the other side of the plate instead of the original plate. And so some would counteract gravity, and you would be able to see this directly through the viewing microscope. Okay. And so he was able to say, oh, yes, these electrons have a charge, and they are able to, by calculating it based on the mass of the drops that were falling through and how fast they were going, he was able to determine what that charge actually was. And so Ernest Rutherford was next, and he found that if you were to take a very thin piece of foil, gold foil, and bombard it with something called an alpha particle. Now, we've talked about alpha particles before, but this is a nuclear particle. It is a common result of nuclear reactions. The emission of nuclear particles. And so it is just a positively charged helium atom, really is what it is. So if you don't remember, this is how you would determine the atomic mass. This is the number of protons. And this is the symbol. And this is the charge. Anyway, so he was able to bombard a thin piece of gold with helium particles with no electrons, and then he was able to see that some would get deflected and some would not. And so what he did by doing this was the alpha particle source would blast this gold foil in the center, and then sometimes you would get a little dot of a detection on different parts of the screen. And so he said, basically, most of the space in an atom is going to be positively charged in the nucleus. Most of the space is going to be empty, but there is a little bit of the atoms, a little bit in the center, but that contains most of the atom's mass, and it is positively charged. And so this is more of a close-up of what that looks like. So the electrons are going to be orbiting the center, and any of the positively charged alpha particles, remember helium 2 plus, is going to go toward the nucleus and then get deflected away from it. Because when you have something that is positively charged coming towards something else that is positively charged, there is a repulsion that occurs where you get them pushed away. So it would be pushed away from that nucleus onto in a different direction rather than going straight through it, or bouncing elastically. So let's talk about what the different parts of the electron are, of the atom are, and remember that this is called the Bohr model. The Bohr model shows the nucleus in the center with orbiting electrons around the outside. And so the number of protons in an atom is called the atomic number, which is the number Z. So the atomic number in the center is what we refer to as Z. So this is actually a pretty good example because this is an alpha particle. Well, it's close to being one. This is a helium atom. Helium atom, you have... if we write out this is A, Z, X, where X is our symbol, A is our atomic mass, and Z is our atomic number, or our charge, then, or our positive charge, our number of protons, then our Z is going to be 2 for this, because the atom itself has 2 electrons. Oh my gosh, 2 protons, not 2 electrons. 2 protons in the center. And so when we're writing this out, we have He, and we're going to put a 2 down there. That tells us that this is helium. And so this is a description of an element. So an element is a substance whose atoms have the same atomic number. So every single element... if you had a fistful of helium, He, a fistful of this gas, every single one of those is going to have the same number of protons. Every single atom is going to have the same number of protons. If you have a different number of protons, you have a different type of atom. They're all going to have the exact same atomic number. They're all going to have the exact same Z. Okay? The neutron. Now, the neutron is a particle that's just a little bit heavier, I believe, than the proton, but it does not have any kind of electrical charge. And so the way that we write this is like this. N with a 1 up there and a 0 over here. Now, remember, this is the mass, and this is the charge, or your Z. You could also put a 0 up here because this is the Z. This is the number of... that's not fair to say a charge. We won't put a charge there. This is the number of protons. There's no protons, there's no charge, and there is a mass of 1. It's about the same mass as that of a proton. So it's got no charge in it. But it does have a 1. So if we are so far looking at this, remember that A is going to be the mass number, which is equal to the number of protons plus the number of neutrons. So far, our helium atom looks like this. We know there's a 2 down here because there are 2 protons. there are 2 neutrons as well, so we can put the A up here, which is going to be 2 protons plus 2 neutrons. It's going to give us an A of 4. So a 4 is going to go up here. Okay, now we don't know what's going to go here yet, but we will figure that out in a second. We'll figure it out now because I don't think I have another slide, do I? Maybe I do, maybe I don't. Okay, we're going to talk about the electron then. So the 4,2He. Now, remember that electrons are negatively charged and protons are positively charged. So the overall charge that I put up here has to be the combination of all of the negative charged atoms and all of the positively charged atoms. And so that's going to be the 2 electrons plus the 2 neutrons, which is basically like saying -2 plus +2. And that gives us a charge of 0. Okay, so this is what we would write. This is the isotopic symbol for a 4,2 helium atom. Okay, so let's get into what we can find on the periodic table. So first, let's define what we need to. So a period is going to be a group of elements that are horizontal. You can think of it like a calendar. If you have a calendar like that, oh goodness, if you have a calendar like this, each period is going to be a week. A week is a period that goes across. A week is 1 period in the calendar, right? That's how you would break that down. Groups, however, consist of the elements in one vertical column. So if we're looking down the periodic table, all of these are in the same group. And that we call them groups because they all behave similarly if they are in the same group. And so we can number these groups from 1 to 18. And so we'll take a look at the periodic table and we'll see that we have 1, 2, 3, all the way to 18. And so you might notice that these don't quite match up. It kind of looks like a little bit awkward. We don't use the same numbers for these, for the lanthanides and actinides, and so we won't really talk about those in terms of groups. But there are some groups that you should know about, the group 1s and 2s. Those are going to be reactive. Group 17 and 16, also reactive. 15, somewhat reactive. 14, it depends. Yeah, so the groups should be known. They also have certain names. We have our alkali earth, our alkali metals, Am. We have our alkaline earth, AEM. We have our halogens right here, our chalcogens, and our pnictogens. That's how that's pronounced. The P is silent, like a pterosaurus, a pterodactyl. That's what it is, a pterodactyl. Same way. And then we also have our noble gases up here, which I always forget about. Okay, so let's get into how we read it. So, the Z number, the charge, or the positive charge, the amount of positive charge you have, is going to go in the top left corner usually. And this is going to be a number that is, it's a whole number that is going to go from 1 to 118. There's no 0. There will never be a 0 up there. A neutron would have a 0, but a neutron is not on the periodic table. The atomic symbol and name are going to go right here. And I apologize for this arrow right there. It's kind of difficult to have this on the other side. But the average atomic mass is something that we still haven't gotten to even at this point. But we will get into it later. But this is going to be an average of all of the different isotopes, which we will talk about in a second, of mercury present. And so that's going to go right at the bottom, and that's going to be the atomic mass. And the electron energy levels are going to be written right here. But again, we will get into that when we get there. The number of electrons, the energy levels, and all that. As I said before, red text is about gases, blue text is about liquids, and black text is about solids. There's only 2 elements. that are liquids. The rest are either gases, but solids are definitely the most popular ones. We can categorize everything into metals, and we can just ignore these numbers for now. I think I might have counted these wrong, and so we can just ignore them. But we have the metals, which make up the majority of the periodic table. Metalloids make up the smallest amount on the periodic table, and nonmetals are going to be whatever is left over. So let's look at where those are. Nope, let's look at what they are. Metals are going to be things that are, you've seen metals before. They're everywhere. They have a luster or a shine. They can generally conduct heat and electricity very well. And you have come in contact with copper, lithium, and titanium. Even magnesium is something that we used last week, something that you should be familiar with as well. If we're looking at the metals, as I said, they make up the majority of the periodic table. So that is the alkali and alkaline earth metals. You have the transition metals in the center. You have, these are called the main group or P block metals. And you have the lanthanides and actinides. They make up all of the metals on the periodic table. When you get to nonmetals, these are also going to be things that you're familiar with, but you probably didn't know the names of. So, for example, most of the liquids that you're going to come in contact with, besides mercury, are going to be metals. Are nonmetals. And so usually they are made of carbon, hydrogen. That's the most common non-metal things that are present. You also have charcoal here, just carbon, and this is an example. Of course, this is a video, but you can't see it. This is nylon, which is made of all non-metals. It's a polymer. It's coming out of a container, being made in real time. And these are going to exist here. So hydrogen, even though it's on this left-hand side, we'll get into why it's over there at some point, but it's on the left-hand side where it's not really considered one of the non-metals. Or it is considered one of the non-metals, but it's not really considered one of the metals, and it's over there for a specific reason. Again, we'll get there when we get there. But then we also have all of these. So these are all of your non-metals. You have this is called the main group or the P block. We have all the ones you've probably heard of: carbon, nitrogen, oxygen. Maybe you've heard of fluorine, all the chlorines, bromines, iodines, all of those, and then all of the noble gases. Good chance if it is a gas, it is going to be a non-metal. Hydrogen as well is going to be a gas. And then we have metalloids. These ones are weird, but again, you are definitely watching something that is using metalloids. These are going to have characteristics of both metals and non-metals. As you can see, there is a shine to this. I believe this is germanium. But there are many of these semi-metals, and they're very good at being able to choose when they conduct electricity or not. So you can manipulate them to be able to define when they will conduct electricity. And so that's going to be this kind of stair-step case right in the middle, along with germanium and antimony right below that line. So just to reiterate, we have this whole side, metals, this whole side, non-metals, and the things that are in between are going to be semi-metals or metalloids. Same thing. Okay, so let's talk about nuclides and isotopes. So for nuclides, we've already talked about this a little bit, but let's go over it just again. This is the example that I gave before. You have 4,2-He. The mass number is going to be A, and this is going to be for a specific isotope. The atomic number is Z, and that's going to be for a specific type of element. And so there are many different isotopes. And let's see if I can go and show you how many isotopes there are. The nuclide chart is right here. And so let's take a look at it. So this is called the nuclide chart. All of these are different. Wow, this is not going to work. But all of these little dots here are different nuclides of an element. So each one of these is going to be a different isotope that you can see. And so let's see if we can find 15N, if it'll work. There we go. So 15N we have right here, but you can see there's 13N and 14N close by. All of these different things are going to have different mass numbers, but the same number of protons. So helium, whether you have 3He, 2, or 4He2, these are both types of helium. They're different isotopes. And so you can kind of see that here. I also wrote it out here. These are different isotopes of the same thing. Okay, so let's continue. We have different isotopes, and I want to remind you guys that you can write this in a couple different ways. So if you want to write the isotope as helium, you could call this helium-3, or you could call this you could say 3He, and sometimes you don't even need the added part where you are going to add the atomic number. And that's because, as I said before, if you have a helium atom, you are always going to have 2 protons present. And so a helium atom is always going to have the same value. So you can write this like this, where you can write it helium 3, or you can write it 3He. Either of those are just fine to do. You can also write it 3He with a 2 right there. But, as I said, helium is always going to have 2 protons, so you don't actually need this 2 right there. So if you have helium, you have that 2 in there already. Okay, so go ahead and give this a shot. I'll give you a moment, and then we'll come back. And I realize now that it's already solved for you, but if we're looking at the nuclide symbol, the only number that we really need to work on here is this right here. So you have the number of protons and the number of neutrons. So the number of protons and the number of neutrons is going to add up to the number that you're going to put in the top left corner. And so that's going to be 88 with 38 protons on the bottom. So this is your positive charge. And this is your atomic number. Atomic number. And so we could also write this as strontium 88. We could also write it as this, 88 SR. Either one is fine. You don't need to have the 38 there, because if it has 38 protons, it is a strontium atom, so it is not important. Okay, so we're going to talk a little bit about atomic weight now. And so one way that we can define this number down here is the atomic mass unit, or the AMU. A mass unit, atomic mass unit, is going to be 1/12 of a carbon-12 atom, and that is how it's measured. So that would be 12C with a 6 right there. Either way is fine to write that. You could write it without the 6, but 12C, we just take the mass of that, which is going to be 12.0000, divide that by 12, and we get 1. And so that is 1 AMU. And so this can change depending on what element you're talking about, what isotope you're talking about, and so that's why it's defined. But really what's important is that we can say that AMU is just about equal to grams per mole, something that we will be using much more often than AMU. Okay. Okay, so let's get into part 2, and we will continue. So chemicals and substances. So I've already defined a molecule and a compound a couple times, but just to reiterate, a molecule is going to have either nonmetals or semimetals only. As an organometallic chemist, I don't really like this definition, but that's okay. A compound is going to have just two or more different types of chemically bonded atoms. But a molecule can have only one type. So a molecule could be N2, a compound would be CO2. Both of these are molecules. Both molecules. But only this one is a compound. Only this is a compound. So otherwise, they're pretty much identical in definition. So molecules are a subset of compounds. That's really what you should take away from here. Okay, so let's talk about chemical and molecular formulas. So when we are talking about this, we're talking about using the elements, the symbols of the elements in a ratio, with certain numbers in order to be able to determine what the formulas are. So this is glucose. It's part of a sugar molecule. You might have heard of the glycemic index if you or anybody you know is a diabetic. The amount of glucose they take in is very important, and so that's what it looks like. But in this, there are 6 carbons. I guess there's actually 7 because of that, but it works out to be 6. Nope, sorry, there are 6. There are 6 carbons present. There's 12 hydrogen molecules, and there are 6 oxygen. 12 hydrogen atoms, 6 oxygen atoms present. For this one, for sulfur hexafluoride gas, we have a sulfur in the middle surrounded by 6 fluoride gases. And so the chemical and molecular formulas of these are going to be SF6 or C6H12O6. And so when you want to write these, this is how you do it. So each of the atoms is going to be represented by a symbol. And so when we're looking at this hexane, we're going to count all of the red atoms. So that's 1, 2, 3, 4, 5, 6. And so we have 6 carbon atoms. And then for the hydrogens, we'll count 2, 4, 6, 8, plus 6. That's going to be plus 3, that is going to be 14 overall. And so that's how we would write it. And so it's important to note that the subscript is going to go after the elements so that you know exactly how many of that element there are present. And so these are some examples of some common ones that are used. We have water. Y'all should know what that is. Ammonia. This is a common cleaning agent, but it's also used in many, many other things. And we have ethanol, which is the active ingredient in alcohol. And so all of these are the molecular formulas of this. We will eventually get to drawing structural formulas. And we'll draw the ball and stick models as well. I might make you guys kits so that you can make your own. But there's all different types of ways that you can represent these. But the molecular formula is what we're going to focus on. And so one type of molecule is called a polymer. So polymer is a long string of, there should be one of those there, a long string of different, molecules that are bound together. So this could go on for hundreds and thousands of different units of monomers. So monomer is going to be just this space in the middle where you have this repeating unit. You have a carbon with 2 hydrogens and a carbon with 2 hydrogens bound together, and that repeats and repeats and repeats, and that is what makes a polymer. And we use these polymers for everything, and constantly we are using them. One example is in plastic, as you can see on this water bottle. This water bottle is made of plastic. And so that is a type of polymer, but also DNA that is in your body. That is another type of polymer, along with many different ones that are in your body. It is not the only one. It is the most widely known one, but it's not the only one. One example of a controversial polymer is the polymer Teflon. So not all these polymers are good. This is supposed to be a PowerPoint presentation, so that's why that's overlapped. But the fluorinated version, where all of these hydrogen atoms are replaced with fluorine atoms, is what makes the nonstick on a nonstick pan. And so this is great, and it's super hydrophobic, which means that food doesn't stick to it. However, it also is very stable up to very high temperatures. However, it is one of the largest sources of microplastics, specifically polyfluoroalkyl substances. So you have PFASs, I guess. That's because once you get it hot enough, it might chip, it might get into your food and stuff, and it can be pretty detrimental to your body, causing blockages, causing cancer, if you use a lot of it. And it also can ruin the environment, so like these things do not break down that well. So if they get into the soil and air, then that can be very detrimental to life outside of your body. As a side note, I like asparagus, but I don't think that much asparagus should go into an omelet. I just noticed that. Anyway, okay, so let's go to ions and ionization. So an ion is what is defined as a particle, an element, an atom, something that has a charge to it. So either a positive or negative charge. This happens from the gain or loss of electrons. So electrons, remember that in our nucleus, we have a positive charge. In the nucleus, we have a positive charge because we have protons, which have a positive charge, and we have neutrons, which have no charge at all. So if electrons are lost and we don't have that anymore, then we have an imbalance of the number of protons and neutrons. Remember that electrons are negatively charged. And so if we do not have equal amounts of protons and neutrons, protons and electrons, then we have a charge. If we have too many electrons, that is too much of a negative charge. And so we get a negatively charged species. If we have too many protons compared to the amount of electrons, then we have a positively charged species. And keep in mind that you do not lose protons. You do not change the number of protons ever. You only change the number of electrons, because if you change the number of protons, then you have a different element. You will no longer have sodium, you will have a different element. So the only thing we can change to make an ion is the number of electrons. Okay, so when you have a negatively charged ion, we call this an anion. Anions are when you have too many electrons. Too many electrons. We are going to, whenever you have a single atom that has a negative charge to it, we end that word in "ide." So we'll use the root for chlorine, for example. We'll say chlorine, the root of this is chlor, and then the I and E part is the rest of it, the suffix, to show that it's not bound to anything. When it has a negative charge, then we change it to chloride, because now it has a negative charge. So negative charged single atoms get "ide." And of course, you guys have you've worked with polyatomic ions, and so we'll explain how that change gets there, but we're not quite there yet. So for single atoms, it ends in "ide." When you lose an electron, then you have too many protons. So if you lose an electron, you have too many protons. Protons are positively charged, so you get an overall positive charge for your atom. You are going to, the way that you would name this is you would just say the word of the element. So sodium, and then you'd end it in the word cation. So if you have a positively charged element, you'd say sodium cation, specifically for sodium, of course. So sodium cation. And as you can see here, we have 11 protons, 11 electrons. There's an overall charge of 0 there. We don't care what the charge is. Well, we do care. It's 0. For the charged species, you have the same number of protons. Remember, we do not change the number of protons. I'll put a P plus for a proton. Don't change the number of protons. But we do have a different number of electrons now. We went from 10 to 11. So that is going to be a difference of 1. And with the protons having more, the protons are positively charged, so we get an overall charge of +1. So for ionic compounds, when you have an ionic compound, this is a compound that is composed of cations and anions, so positively charged and negatively charged things. In order to have a completely neutral species, you have to have an equal amount of charge. So the formula of an ionic compound is going to gives us the smallest possible integer between these. So you would not write, for example, Na2Cl2 because these do not have the simplest integer. So we would divide both of these by 2, and it would be Na1Cl1. But remember, we do not care about the number if it is a 1, so we go to NaCl, and that's it. The formula unit of a substance is the group of atoms or ions explicitly symbolized in the formula. So this is very similar to a molecule, where we would say C6H6 for benzene, which is a molecule. We would say NaCl for sodium chloride, which is a ionic compound. So basically what this is saying is that for non-ionic compounds, these are called molecules, and the equivalent name for a molecule for an ionic compound is the formula unit. So, okay. And so this is what we see when we look at compounds, when we zoom in really far. So this is a chunk of salt. This is this wonderful stair-step pattern that you also see with bismuth. But you also have, if you were to zoom in even further, you would see that each of the ions, this is a Cl, a Cl minus ion, and the Na plus ions, they're arranged in such a way that they are evenly spaced in a repeating pattern. And this is what makes a crystal. This is what a crystal looks like if you zoom in far enough. And I have made plenty of crystals, so if you guys ever want to see one, just let me know. I'd be happy to show you. And yeah, and so this is just a different view of the exact same thing, but it's called a it is called a space filling model. It doesn't really matter though. Well, let's continue. Okay, so for determining formulas, if you have no charge, then you will write nothing up here. There is no charge that comes up here when there's no charge for the atom. If you have a negative charge, you get a little minus symbol. If you have 2 negative charges on the same molecule, then you get a -2. 3 charges would be -3. Same thing for positive charges. So if you have H3O with a positive charge, you put a plus in a superscript. The subscripted numbers say how many of those elements you have, and it's specifically only the element that is to the left of it. So this 3 belongs to the H. It does not belong to the O at all. The O does not get a 3. It's just the H. Same with this 4. The 4 goes directly to that O. It does not go to the MN. Okay? That's something that is very important to remember. So the subscripted numbers say how many of that element there are. So there's 4 in KMNO4, for example. If there's no number, then we assume that number is 1. So K1MN1O4. That is how that would work. Okay, so for predicting the charges of these are fairly straightforward for the most part. So if you have an element here, then you are going to be able to predict the charge of that element. And that's because all of these elements want to look like noble gases. Noble gases over here, they all want to look like noble gases. So keep in mind, for a noble gas, there is no charge ever, pretty much. We'll get into some examples later on where there is a charge for xenon, but that's it. And so they all want to look like noble gases. So what they do is they will either lose an electron in the case of the positive charge, so that the protons have a dominant charge. And the number of electrons that they lose is dependent on how far away from looking like a noble gas they are. So what I mean by looking like a noble gas is, let's see if I can zoom in real quick on neon. So neon, for example, Ne has 10 protons, and we don't care about the neutrons because they don't add to the charge at all or take away from it. They don't affect the charge. It also has 10 electrons. And so 10 protons with a positive charge, 10 electrons with a negative charge, that gives us 0, an overall charge of 0. But really, the magic part of this is the number 10. It really wants to look like it has 10. And so if you have a fluorine atom right here that has 9 protons and 9 electrons, in order to look like neon, it's going to add 1 electron. And so that's going to give us 10 electrons. So we have a -1 charge. Now that we've added an extra electron, we have 1 more electron than we do protons. We have 10 electrons, and we have 9 protons. And so 9, positive 9 minus 10 is going to be -1. And so we get this -1 charge. Same thing we can do with oxygen. Oxygen's going to pick up 2 electrons and have 10. So positive 8 minus 10 is going to be -2. And so we get a -2 charge. Nitrogen, positive 7 minus 10 is -3. And so we get that. So those pick up electrons on the right-hand side. And so I'll write that down here. These pick up electrons. On the left-hand side, the opposite happens. So take a look at the number, let's say sodium. Sodium has 11 protons and 11 electrons. If we, the closest element that is a noble gas is neon, because it has 10 electrons. And so rather than adding any electrons, it is more favorable, it's more energy efficient for that sodium to lose an electron. And so sodium would then have 11 protons and 10 electrons once it lost one of the electrons. And so that would be 11 minus 10 equals +1. And so we have a +1 charge there. Magnesium does the exact same thing, but with 2 electrons so that it can have 10, and so that would have a +2. Scandium, yttrium, and all of the lanthanides and actinides also do that, but I didn't show them here because, again, it can get confusing with that many. But what about ones over here? So we have aluminum. Well, aluminum does the same thing. Aluminum with 13 electrons and 13 protons. In order to get to 10, it has to lose 3 electrons. So 13 electrons minus the 3 that it needs to lose is going to be 10. And so it's going to lose 3 electrons, and so it has a plus 3 charge. Now you have 10 electrons and 13 protons. That means you have 3 more protons than you do electrons. Protons are positively charged, so it has a plus 3 charge. Okay, so if those pick up electrons, these ones lose electrons. It also might help to note where the metals are. So I already talked that this is the line that separates the metals from the nonmetals. Most of the nonmetals are going to have a negative charge. So I'll write that in yellow because it's a dark background. Nonmetals usually have negative charges. Okay. Metals have positive charges. And so the odd ones out here is I did not cover the center area. I didn't cover the center area, and I also didn't cover these are called congeners of carbon. And so the carbon and its group, all of the ones that are like it, can have a very different, they can have different charges. Their charges can go from -4 to +4. So that's why I didn't put them there. They're very versatile, and this is what gives us life. The fact that carbon is able to have a charge from -4 to +4, it has that much wiggle room, makes it very useful for life in many ways. But it can make many different compounds. It's very flexible, and so that's why I say nonmetals usually have negative charges. Nonmetals can have positive charges as well. Transition metals we'll get into in a second, but these can also have very different charges. But these charges over here are always going to be the same ones, 1, 2, and 3. However, these are not the magic numbers. We'll get to that in a second. Okay. So, if we want to use formulas to predict the charge, here's how we do it. You guys have seen me do this a lot lately. But we're going to go like this. We're going to split it in half. Find the easiest one to identify. Find the easiest charge to identify. And so I already know that that's going to be oxygen, but copper is right here. Copper is a transition metal, so it could have different charges. We don't know. We don't know what the charge is going to be. But oxygen is in the -2 area, so it's definitely going to have a -2 charge, especially when it's with oxygen. So we'll put a -2 here. We'll say -2 for that. And keep in mind that we would have to multiply it by the number of oxygens that there are, but there's only one oxygen. There wasn't a 1 there before because remember, we do not have to put a number if there's just a 1. But we'll multiply that by 1, and we get a -2 charge overall. So -2 overall. So you'll notice that there is no charge associated with this compound, which means that the entire compound is neutral, which means that the charge of copper has to be something to balance that out. So we will put a +2 over here because that's the only thing that when multiplied by 1 is going to give us the charge that is going to satisfy the -2. So there's a +2 overall. Okay. So we split the ion in half with that bar. We found the easiest one to determine what the charge is, and then we satisfied the charge on the other side. Okay, so here are some rules of thumb. If the atom is a metal, it's going to have a positive charge, pretty much always. If it's a non-metal, it can have a positive charge, but it is very, very likely that it will have a negative charge. Charges tend to cancel out, and if they don't, then the whole substance has a charge. So for this one, NaCl, we have no charge present, which means that all the charges cancel out. For this one, we do not have not everything is canceling out, and we know that because we see a charge right here. Okay. All right, so chemical nomenclature. We did do an entire lab on this, but so I won't touch on it too much, but I will explain the more difficult ones. So we have inorganic compounds and organic compounds. So let's start with the inorganic ones because they're a little bit more complicated, and the organic ones are going to be organic, or the molecular compounds are going to be a little bit easier. So for naming compounds, you name the cation, you just give it the whole name, and then you name the anion. So for NABR, that is sodium brome, and you take the root and then you get rid of the INE, so this is bromine, but it has a charge, so we are going to name it bromide. It's just the one element. There's no oxygens attached to it. So this is sodium bromide. Magnesium, this should be a 2+. Magnesium, you just say the name of the metal. You say the root of the anion with IDE at the end, so magnesium oxide. Aluminum chloride, same thing there. So that's for one single element at the end. As the anion. And I'm going to continue this video because I don't want to make another one, an extra other one. Okay, so we'll keep going. Atoms, molecules, and ions. So these are some of the things that I didn't go over before, but the noble gases have no charge. This is why we are trying to we try to have these elements look like the noble gases, and there's a lot more reasons than just them not having charges, because obviously if you are going to have a fluorine atom that gains an electron so that it can look like neon, a fluorine atom gaining an electron will look like neon, then it's going to have a charge because it has 9 protons and it will have 10 electrons, and so that will give it a charge. So, but for the noble gases altogether, they're going to have a charge of 0. We also discussed isotope nomenclature. I just added this slide so that we could describe the element names and the element symbols without the positive charge present. We discussed ionic compounds, but organic compounds we haven't really talked about. An organic compound is something that contains an atom of carbon bound to an atom of hydrogen at least once. So N2, not an organic compound. CH4 is an organic compound because it contains at least one bond from carbon to hydrogen. And again, we haven't gotten into bonds yet, but just the fact that these are together, that makes them an organic compound. Surprisingly, H2O is not an organic compound, even though it sounds like it should be, right? Water, it sounds like it's organic, but it's actually not. So, as I have here, H2O is not an organic compound. It is an inorganic molecule. But since CH4 makes bonds from carbon to hydrogen, we do have it's called a hydrocarbon. It's also called an organic compound. This is what cows fart and burp. And it is also what comes out of your stove because it is very flammable. So you could actually light a cow's fart or burp on fire, which is kind of crazy. You could also write. This is also what you fart, so you could also light your own fart on fire. I am absolutely not condoning that. Please do not do that, especially not in my classroom. Okay. Some example functional groups. We have okay. So a functional group. Again, we'll talk about this later more, but just a quick rundown. Functional groups are the reactive portions of organic molecules, and so these are some examples. You have an OH or a hydroxyl group. Those or hydroxide or an alcohol, they go by a lot of different names. That is just an OH. You have an ether. Honestly, it's not even really worth talking about this right now, so I'm going to keep going because we are not going to use that for quite some time. All right, so we've already done this one, and so we will continue from here. So if we wanted to find the charges from these formulas, let's go over how we do that. So there is a method that you can use that I've discussed before where you do a crossing type thing. And it does not always work, but it's worth trying first because it might be very easy to get the correct answer. And so what you want to do is you're going to you circle one of the numbers and point it up toward the other side of the element. So let's start with the anion. We'll take the 2 from the anion and point it toward the cation. We'll take the 3 from the cation and point it toward the anion. And so what this ends up being is Zn. We'll take the 2 from over there, and since it is the cation always comes first. It's also a metal, so you know it's going to have a positive charge. Is going to be a zinc 2 plus. So the 2 is going to come from the nitrogen, and the plus is going to come from the fact that it is a cation. For nitrogen, we'll take the 3, and it's an anion, so we know that it has a negative charge. So we'll say N3 minus. And so how this works out is that if we were to break it down again and go like this, we have something over here. So if we're going to do it by the classical rules, rather than cheating and just using, it's not cheating, it's just a shortcut. If we were not able to tell exactly what the charges were here, then this is what we would do. So nitrogen, the most likely charge of nitrogen, is going to be 3 minus. And so we can take a look back quite a few. Let's see. Oh boy. I don't know why it skipped me so far ahead, but so if we are looking back to where we started with, which is not present. Oh, okay, so if we're looking back to where we started with, nitrogen is going to be a 3 minus charge, okay? And so that's the most likely one. So we'll stick with that. We're going to assume that it's going to be a 3 minus charge, especially when it's bound to a metal, because I have a 3 minus charge. And so it has a 3 minus charge, and there's 2 of them. We'll put this 2 down here to say that we're multiplying that 3 minus charge times 2, and we will set that equal to what that is equal to. So that's a -6 charge over here. Now that means that all of the charges on the left-hand side need to counterbalance a -6 charge. So we have 3 right there. We'll multiply that by some number, and it has to be equal to +6. And so 3 comes from right there. What is the number that has to go here? Well, that's going to be +2. So +2, 3 times +2. So this is just to clarify, the number of atoms. This is the charge. And this is the overall charge. And so 3 times 2 is +6. So we know that Zn is going to have a +2 charge. N3 minus is going to have a -2 charge. Or -3 charge. Okay, go ahead and give this next one a shot for a second, and then I will continue. Okay, so I'm going to do the crossing method first, and then the other method. So let's put this over here, and this over here, and we have CO, too big of an O, CO with a 3 plus charge, and C with a 4 minus charge. Remember, I said carbon can have a positive 4 or a negative 4 charge. It depends on what it's bound to. When it's bound to a metal, though, it's going to have a negative charge. So we have a 3 and a 4, and that is how that works. And we can also break it down the other way and do it like this. So we'll put a line, and then we will say, so the reason that we know that this carbon is going to have a negative charge here is going to be because carbon is a nonmetal, and when you have a metal bound to a nonmetal, the nonmetal is going to have a negative charge. And so since it would have a negative charge, if we look at the periodic table, we have it is right in that center. So it could have a positive charge. It could have anything between negative 4 and positive 4. We're going to assume that it has a negative 4 charge. And so we know that we have a negative 4 right here. We will multiply this by the number that is present. So that's 3, and that gives us negative 12. Over here, we know that we're going to end up with negative 12 or positive 12. But we don't know what the charge is on this, but we do know there's 4 of them. So 4 times some number is equal to positive 12. And so that number has to be positive 3. 4 times positive 3 is positive 12. And so the elements we have are CO plus 3 and C minus 4. Okay. And so just to be clear, I'll show you one more example where you can't use the crossing method. So MnO2. Okay, so manganese can have a charge anywhere from +1 to +7. It's one of the most versatile elements that there is. And so we just have to figure out what that one is. We'll break it down in the middle. And we will say oxygen. Oh, well, we won't do this yet. We'll do the crossing method first. So we have a 1 right here and a 2 right there. So we would cross this, and we would say that manganese has a 2 plus and oxygen has a 1 minus. But we know from our chart that oxygen is 2 elements away from having a having 10 electrons, and when it's bound to a metal, it's going to be as negatively charged as possible. So we have oxygen. Oxygen is usually going to have a 2 minus charge, and so we can assume that that is not going to work for this. Oxygen can't have a -1 charge because when it's bound to a metal, it's going to have a -2 charge. So that doesn't work. Instead, what we can do is we will assume that it's going to have a -2 charge. We'll multiply that by the number of elements that there are, and then we will get a -4. So that'll be a -4 charge overall, which means that manganese, since there's only one of them, it's going to be +4 times 1 equals +4. So manganese is going to be +4, and oxygen is going to be -2. Okay. All right, let's continue. We have naming of compounds, which we have covered, and these are for binary compounds. So a binary compound is a compound that it consists of just 2 elements. So and we've already done this. So naming the element, you just say the name of that element, and then you say the root of the anion with IDE, or ide, at the end. So that's mercury chloride. All right? And so I'll give you a second to give these ones a shot while I change this to the single page mode, because it's a lot easier to deal with that way. Okay, so to name these compounds, we'll start with this. So the name of Na is sodium. Then we'll use the root, FLUOR, spelled weird, I know. And then IDE is what we'll end it with, sodium fluoride. Now this is barium. And we will take the root, SULF, and then end it in IDE, sulfide. That is rubidium and oxide. And notice that I did not include the 2 there. For metals, for ionic compounds, we don't need to say how many of those how many of the cations or anions there are. So for ionic compounds, no need to say that. I'll write that there. Ionic compounds do not need prefixes, let's call them. Prefixes to determine the number of atoms. Okay, rubidium oxide. And we don't need to do it for the metal or the non-metal. So this would be magnesium phos, PHIDE, phosphide. If you wrote phosphoride on an exam, then I would accept that, because the root is annoying, and then sometimes it changes depending on what it is. So, but generally it's going to be the first few letters followed by ide. But phosphorus is a bit different. Okay, so it gets a little bit more complicated when we get into the D block elements. So these are the transition metals. These are going to be the ones that are in the center of the periodic table. In general, you should not assume the charge of these elements. As you can see for ruthenium, you can have anywhere from a -2 charge to a +8 charge. These are very rare. The most common ones are bolded there as +3 and +4. But as a reminder, oxidation state just means charge in this sense. But you never want to assume what they are. And so what we'll do is I will show you which ones can have different ones and change a lot. So anything in the middle is likely going to have a different charge, a variable charge. I included scandium and yttrium here as well because they can have different charges. It's incredibly rare, but that's what I did my research on, so I'm partial to doing that. But I probably won't put those on a test. But you can also, for the metals that are part of the main group or the P block, which we'll get into the names of those as well, these can have different charges too. These can have different charges, and so it's important to specify which ones they are. Keep in mind that polonium also probably will not be talked about because as its atomic mass is in parentheses, that means it is a synthetic element, and it probably will not be spoken about too much in terms of compounds because they're so radioactive that those compounds don't really exist, and I want to keep some degree of realism. Okay, so the charges can vary for the heavier of the metals and of the transition metals. And so when we do that, we have to specify. But there are some cases, and I call these the magic 3. These are what I've been calling the magic 3 so far. So aluminum is always going to have a 3+ charge. Even though it's a metal, it's going to have that. Zinc is always going to have a 2+ charge, and silver is always going to have a 1+ charge. 3, 2, 1 alakazam. And so these are going to exist in this area right here. You have silver, zinc, and aluminum all in a row. Silver has a +1, zinc has a +2, aluminum has a +3. So please remember these because they are going to come up quite a bit. And so the next rule is going to apply to these. So it's important to know that. So when we name the binary compounds with these tricky metals, you have to say what the charge is. You have to define what the charge is because there are many different metals. There are many different charges that these metals can have. If the metal only has one charge, like yttrium 3 or aluminum 3 plus, or zinc 2 plus, or Ag1 plus, or the magic 3, if it's one of the magic 3, or if it is something that only has one charge, then you do not have to say what the charge is. So that goes for, let's go back. We have already defined some that are going to have consistent charges, and those are going to look like this. So if you have a metal from the alkali metals, a metal from the alkaline earth metals, group 1 or 2, those are always going to have a consistent charge, so we don't have to name what they are. If you have one from group 13, or if you have zinc, or if you have silver, those are going to be always +3. Scandium and yttrium as well, they can vary. As I said, I'm not going to put those on an exam, so don't worry about that. Or for this reason, I won't put them on an exam. I might put them on for a different reason. Okay. Let's continue to talk about these. So if it only has one charge, then you do not have to put Roman numerals there. And so just so you know, these are how Roman numerals work. I realize I never actually explained this, but let's go like this. I will go back to this here, and we'll talk about this. So I'll write 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're not going to get a charge that's greater than 9, but I'll put 10 here as well. And so when you're writing Roman numerals, this is what you want to do. You want to have an I. An I means 1, so that's an I. When you have 2, that is going to be 2 I's together. 3 is going to be 3 I's together. Now, when you put an I before a different number, that means you subtracted from that number, or before a different letter, I should say. So if you have I next to a V, that is going to be 4. So that means that is 4. V is for 5. So we'll keep going like that. That's V. So that's going to be 5 minus 1. And so that's how you get to 4. So it goes 1, 2, 3, 5 minus 1, and then 5. I know it's confusing, but if you need help with that, that's okay. You can just let me know, and I'll let you know about it. So you're only going to ever have 3 I's at a time. So that means that the next one is going to be V I. You're going to add it. If it's to the right, you add it. So that'd be 5 plus 1 to get 6. V I, and then VIII for 7 and 8. So that would be 5 plus 2 and 5 plus 3. And then, so we've gotten the maximum number of I's we can include, so we have to start subtracting from the next number. Now let's go to 10 real quick so we can see what that number is, but that number is X. X is 10, and so 9 is going to be IX, like that. And this will continue. If you are curious, I would look up the Super Bowls, because all of the Super Bowls are numbered like this, and if you look up the numbers of the Super Bowls, you will see exactly how that correlates for much higher numbers. So let's continue. We have this now. So, name the following transition metals. Okay, I'll give you a second. Give it a shot. And then we'll continue. So, first let's start with this one. Ag, that is a transition metal. However, it is one of the magic 3. And so nitrogen, when it's bound to a metal, is going to always have the same charge. It's also, silver is also one of the magic 3, so we do know that its charge is going to be +1 because that is the way that it is designed. So this is the way that we will write it out. If we were to split it up by ions, that'd be Ag +1 and N with a 3-. So Ag is silver. So we would say silver. And then N3- is nitride. So nitride. This is an explosive compound. AgN3. I've made it on accident once. It's not so bad though. Okay, and then NiO. This is another one of the transition metals, but it's not one of the magic 3. Remember, the magic 3 are going to be Ag, Zn, Al. If you have difficulty remembering that, it goes 1, 2, 3, and you can imagine that there is a magician named the Great Agzanal or something like that. And so Agzanal is your great magician. 1, 2, 3, AgZnAl. And so nickel is not one of those magic 3. So we should define what it is. So first, oxygen, when it's bound to a metal, is going to have a -2 charge. There's only one of those, so the overall charge is -2 on that side, which means that nickel must be a +2. So we would say nickel has a +2 charge. Oxygen has a -2 charge. So we would call this nickel. And since we didn't know what the charge was, it's a transition metal, it can have a variable charge, we have to define what that charge is. And so we'll put a 2 there, and we will then say oxide. So it's nickel 2 oxide. That's how we would define that. Nickel 2 oxide. Okay, zinc. Zinc is one of the magic 3, so it's a +2. So we don't have to put the Roman numerals there. So we say zinc oxide. Again, oxygen is going to be a -2. We have Zn with a +2. That's a 7. We have a +2, and we have oxygen with a -2. All right, and then we have RuO4. Ruthenium is another transition metal, and so I'll show you where these are in just a second, but ruthenium is going to have oxygen bound to it. When oxygen's bound to a metal, it's -2, so that's -2 times 4. That gives us a -8 overall charge, which means that ruthenium, since it's by itself, is going to have a +8 charge. Okay, and so that means that we have ruthenium 8 is going to be VIII, and then we will put oxide. Ruthenium 8 oxide. That's how you would say that. Okay, and so let's just go back real quick. So silver, nickel, zinc, and ruthenium. Where was it? Okay, so silver, one of the magic 3, is going to have a +1. Nickel, since it was bound to oxygen, would have a +2. And ruthenium is one of the crazy ones. It can have a +8, so we'll have a +8 charge there. Okay, moving forward. Now, this is the one that people trip out on a lot, but a polyatomic ion. So a polyatomic ion is an ion. Let me just make sure. Okay, cool. A polyatomic ion is an ion consisting of two or more atoms that are different, that are chemically bonded to each other. And so these are sulfates, phosphates, carbonates. These are all examples, and many are called oxoanions. And so the reason for that is because they are anionic, meaning they have a negative charge, and they are oxo, which means they have oxygen on them. And so these are the different types of anions. You have carbonate ions with a -2 charge. Notice that all of these have oxygen on them. These are all oxo ions. And they are each going to have their normal number. So a normal number of oxygens and this is what we're going to define as the 8. So we have 8, 8, 8, 8. This is how you find what those normal numbers are. So it's not always going to be 3 like it is for carbonate. We also have PO4, which has an 8 as well. It's whatever the normal number is. And so we'll describe that over here. We'll get into naming of acids in just a second. But for naming the polyatomic ions, you'll say the first part of the element name, and then the suffix determining what kind of element that is. So it depends on the number of oxygens. Each polyatomic ion has a normal number of oxygens. This ends in 8. Okay, so these normal numbers are going to change. Or sorry, they're going to change depending on what the other element is. But one oxygen below the normal number ends in ite. 2 oxygens below ends in ite, but also has the prefix hypo. So it's hypo something ite. 1 oxygen above this is going to be per something 8. And we're not going to get to, there are none that I know of that have 2 oxygens above the number of oxygens. So per something 8 would be the highest it goes. And this is very, very important. So changing the number of oxygens does not change the charge. So if you have ClO4, which we would call with a minus charge, perchlorate, and ClO3 with a minus charge, which is chlorate. Notice how they both have the same charge. We have a minus and a minus, but they have different numbers of oxygens. We'll get into why that is exactly, but I want to talk more about what the normal ones are. So this is an example, and I would like you guys to make your own version of this chart so that you can know exactly what the normal ones are, how you can change them, and stuff like that. So we have the normal for chlorine, that's going to be a -1 charge. For carbonate, we have a -2 with 3 oxygens. Nitrate is a -1 with 3 oxygens. Phosphate, sulfate. Okay, so there's something else that I was alerted to that I want you guys to, that might help you when you're doing this. So for some of these, the root element will have the same, the 8 version of the root element will have the same charge as if it didn't have any oxygens. So what I mean by that is chloride, Cl minus, is going to have the same charge as ClO minus and as ClO2 minus and as ClO3 minus, etc. Well, really ClO4 is the last one. But they all have the exact same charge. The same charge is present on each of these. So since the same charge is present on each of these, that is one way that you can remember that. Now, that's not always the case. You can see for carbonate, carbon can have a very different charge. It doesn't really matter. But for nitrate, again, that also is the same. It also does not have, nitrogen is going to have a 3 minus charge for nitrogen. Nitrate is all of the nitrates and nitrites. This should be a plus. This should be a 2. Nitrites should have a 1 after instead. Phosphorus, though, and sulfur behave this way. So phosphorus is going to have a -3 charge, and phosphide also has a -3 charge. This is also wrong. That should be 3. Nope. This should be 3. PO4 up here. -3. And then this should be 2. There we go. Phosphate, H3PO4. Nope, just kidding. Oh my goodness. All right. Anyway, I'll release something that explains exactly what I mean right here. But this definitely should be 3. Okay, and then SO4 also does this. S would have a -2 charge. And so SO4 also has a -2 charge. Sometimes it just works out like that. But we'll keep that in mind. Okay. And so this was naming the ions in green. And I'll go ahead and do that with you right now. If you want, go ahead and take a chance real quick, and then we will name them. Now remember, this is supposed to have 1 less oxygen. So that should be a 2, and that should be a 3. Let's see, did I do that with that? I didn't do it with that one. Okay, good. So, let's name the ones in green. We have per with the root going in here. The root is also going to go there, and it's going to go right before the 8, or the ite or the hypoite. So we'll say that this is perchlorate. This one would be hypochlorite. Over here we have carbonate. We have nitrite when it has 2. Phosphite and sulfate. Okay. All right. So we want to treat these all as an entire ion. Okay. So we have this. Anything in parentheses is going to be treated as an entire ion. We also have the Cr, which is not in parentheses, but it is a transition metal. And so we want to figure out what the charge is. So let's break it down. We have Cr3. We have PO4, 2. Now phosphate, well, I screwed that up, but phosphorus is going to be one of the ones that we have a 1-to-1 correlation with the P with its twin that does not have any oxygen. So P3 minus. So phosphate is always going to have a minus charge. It has 4 oxygens, and so if we go back, 4 oxygens is in the normal range, so that is going to be phosphate. Okay, and so we want to know next what the charge is on chromium, because chromium is a transition metal, and so we need to know what that's going to be. So PO42, each one of these is a -3, and so we'll multiply that by 2. The 2 goes down here, and that is going to be -3 times 2 is -6. Chromium, it has to add up to +6. We know that there are 3 of them, so that's going to be 3 times some number equals +6, so that's going to be +2. And so we would say chromium 2 with Roman numerals phosphate. Chromium 2 phosphate. Okay. So go ahead and give these ones a shot. It's a mix of different binary acids and other ones. And I didn't expressly say what this is right here, this OH, but this is also a polyatomic ion, and it's called hydroxide. Okay, give it a shot, and we will go through it. Okay, so we have LIBR. LIBR, well, that's going to be lithium. Lithium is a group 1 metal, so we don't need to put in the charge for it because it is always going to have a +1 charge, so we just need to have the ending. So that's lithium bromide. This is cesium. Cesium is also a group 1 metal, so we can just say cesium, also spelled like this, CAESESIUM. I'll accept either. And OH is hydroxide. Hydroxide. Okay, now we have this. K is a group 1 metal, so it's going to have the same charge. We also have ClO3. And so ClO3, let's go back to our chart real quick. ClO3 is the normal version, so we would say potassium chlorate. All right, and then we move on to the next one. Calcium is a group 2 metal, so it'll always have the same charge. This, however, is not phosphate, so let's go back and see what we have. We have phosphite, PO3. I know I scribbled that in, but it's phosphite. So this one is going to be calcium phosphite. Now, if you want, please notice that we do not care about the numbers here. We're not going to say calcium diphosphite. We're not going to say tricalcium diphosphite. We're not going to say tricalcium phosphite. It's just calcium phosphite. Okay, now for this last one, we have Fe right here. And so Fe is going to be a transition metal. It's not one of the magic 3, and so we need to know what the charge is. So we will have to look at this. SO2, however, is that the normal number? No, it is not. So we'll write one in here. SO2 with a -2 charge. So that would be hyposulfite. So that would be hyposulfite. We know what that is. Now, there's 2 ways we can go about doing this. And let's explore them both. So we can do the normal way, where we take Fe2SO3, we break it down in the middle. Remember, this entire thing in parentheses is what's going to be the anion. And so we have 3 over here and 2 over here. Let's do the crossing method. That is fine to do here. It does happen to work out. And so this would be Fe3 plus SO, or not plus, and this would be SO2, 2 minus. And so this is allowed here, but it isn't always allowed. You want to check the crossing method first to make sure that it makes sense. Then go and try it the other way, because the crossing method is a shortcut. So you might be able to take a shortcut, but let's make sure that we're not. So we know that we're not messing up. So we know that SO2 is going to have the same charge as SO4, and it's going to be 2 minus. And we know that there is there are 3 of them. We don't care about this 2 in here because the 2 is going to just be applying to this oxygen, not the entire hyposulfite ion. So we have a -2, and we're going to multiply that by 3. It gives us an overall -6. So iron there's 2 of them, so 2 times x equals +6 to balance that out. And so x must be 3 plus. And so we would call that Fe 3 plus, and we would say iron 3 hyposulfite. Now let's move on to these ones, and we're going to translate them. So lead is not a transition metal. Let's see. I should just memorize what the number is to go back real quick. Where are you? There we go. Lead is not a transition metal, but it is in a category that could be many different things. So lead is not a transition metal, but it's also a heavy metal. It could be many different ones. And let's see, I have another one. Yeah, this. Okay, so lead is one of the ones that can have a varying charge right there. I'll go back to slide 15 in the future. And so what we'll say is that we need to figure out what this is. So first, we need to figure out what nitrate is. We'll go back to nitrate. The 8 one is the normal one ends in 8, and so we have NO3 with a 1 minus charge. So NO3 with a 1 minus charge. Now PB is lead, and it doesn't actually say which one we need to do. However, I do know that lead typically has a +2 state, and so this is actually a mistake on my part. I should have said exactly which one I was looking for, but this is going to be lead 2. So PB 2 plus. How many of these NO3s do we need to multiply for these charges to satisfy? We have a 2 plus here, a 1 minus here, so we'll put a 2 right there, and we get PB NO3 2 for that. Now cobalt is given that it's a 2 plus, and chloride means that it is just the chlorine by itself with a negative charge. And so I'll write this down here. Let's see. Yeah, I'm running out of space on this one. So cobalt is CO, and chloride is Cl with a minus charge. We know we have a +2 charge because it's given in the Roman numerals here. So in order to satisfy that, we will have to multiply this by 2, and we get out COCl2. All right. Now we have sodium perchlorate. So perchlorate is going to be 1 more than the normal number for chlorate. So chlorate is ClO3 with a 1 minus charge. So perchlorate is going to be ClO4 with the same charge. Sodium is a group 1 metal, which is Na with a plus charge. And so we have a 1 plus and a 1 minus, and so we just get NaClO4. There we go. That's it. Okay. All right. So binary acids and oxoacids. So when we're talking about acids, we can do the exact same thing. So for binary acids, we're talking about acids that consist of H and only one other element, and there's only a few of these. There are really only, let's see, I think 4. We have HF, we have HCl, we have HI, and we have HBr. And those are the only 4 that are available. HF, HCl, HI, and HBr. You could make an argument that there are other ones as well, but for now, those are the only ones that we're going to be considering. An oxoacid is one that has a polyatomic ion and H. And so remember, when we're talking about acids, we have hydrogen in front. That's because it is a cation, and that is where we're going to put it for for acids. Oxoacids are going to contain hydrogen and oxygen and another element that we'll refer to as the central atom. And as I said, for these are our these are our binary acids. There are some other ones if you want to argue it, but I don't want to hear it if you want to argue it. So we have hydro blank ic acid. That's how we are going to name these. So for HCl, that would be hydrochlor. That's our root ic acid. Hydrobromic acid. Hydroiodic acid. Hydrofluoric acid. So these are the acids that we are going to, these are the binary acids. So honestly, these might just be worth memorizing. For oxoacids, we do not use the hydro part. That does not come into play. We just say the root, and then we say if it ends in 8, so if it has the normal number of oxygens, we will change that to ic acid. So that would be for a nitrate, that would be nitric acid. For sulfate, that is sulfuric acid, if you will. If it ends in ite, then you change it to us. So let's do the same thing that we did before. This chart is to help you out. So for perchlorates or for per blank eights, we do the exact same thing. It's just if it ends in 8, we change it to ic acid. So perchloric acid. So perchloric acid. And remember, the difference between this and chlorate is that this is going to start with an H. So HClO4. That's how you would write perchloric acid. For ClO, that would be hypochlorous acid. If it ends in ite, you change it to us. So ite becomes us acid. Hypoite becomes hypo-us acid. For carbonate, carbonic acid. This is what's going to give carbonic acid, so that is going to be H2CO3. If you've ever had bubbly water before, it has a slightly acidic taste. This is what gives it that taste. This is supposed to be A2, and this is supposed to be A3. Nitrite would become nitrous acid. Phosphite becomes, very annoyingly, I don't like this one, phosphorus acid. I don't like it because it straight up says phosphorus in there. We've remade the word phosphorus. We broke it apart and remade it. And then we have sulfuric acid. Sulfuric acid. And so you all have access to these slides. I recommend, if you want to practice this, make one of these tables on your own, or you can take this one and try to name all of the ones that I didn't name. Okay. All right, so that's how you do it. That's how you do it for acids. And I'll just actually write in. We have HNO2, and we have H3PO3, and we have H2SO4. So an H plus is going to take the place, it's going to satisfy those charges, and that's why you get these. Okay, so for molecular nomenclature, it's honestly a little bit easier, I think. You just need to know what the different the prefixes are. So for these, you're going to say for binary molecular compounds, you say the name of a prefix, then the name of the atom, and a prefix, then the name of the second atom, and then you follow it with "ide" instead. And so let's get into what that means. Compound has names in the order given in the formula. So this would be, well, I'll keep going. So the first element is named using the exact element name. The second element is named by writing the name of it with an ending "ide." And so these are from Greek. So let's see. Yeah, let me outline them for you right here. Actually, I'm going to use this again. So for naming what are these called? Molecular compounds. These are the prefixes. So if you have one, we name that mono. And I want to preface, don't use for the first atom. And I'll give an example of this in a second. For 2, you're going to use di. These are the prefixes. So these come before what you name the element. 3, tri, like a triceratops. 4, tetra, like if you've ever heard of Tetris. The reason it's called Tetris is because each of the pieces have 4 different blocks into them. They're called tetrominoes because they have 4. 5, penta, like the pentagon, has 5 sides. 6, hexa. I don't got one for that. 6 hexa just means 6. 7, hepta. I do like these two because 6 and 7 both start with the same letter and kind of sound kind of similar, just like hexa and hepta. 8, octo, like an octopus, or an octagon, like a stop sign. 9, nona, and that one's pretty easy because it kind of sounds like 9. And 10 is deca, and this is like a decade. A decade is 10 years, so we use 10 for deca. And so for the first one, you do not use it for the first atom. So what I mean by that is if you have CO2 that has 1 carbon, 1 C, and 2 O's. So if your compound starts with only one of a type of thing, then you just say the name of that. So carbon, and then we're looking for di, because there's 2 of them, dioxide. Okay, let's go back to the part we were at before. All right, so a prefix is given for each of the words. For example, SF4 is sulfur tetrafluoride, so that's going to be sulfur. You don't put mono in front of there. And then tetra means 4, and fluoride means fluoride. And then you also have the IDE because it's just that one element. And so sometimes you can drop the vowel, the final vowel for a prefix. I don't really care if you do that or not. So if we wanted to determine the name of this, we have P4O6. So we have tetra, as it says below, and then we'll name the entire name of the element, phosphorus. And then we have O6, so that's hexa. But you can drop the you can drop the A and you can just say hex, and then you would say oxide. So we have tetraphosphorus hexoxide. You can also say hexaoxide. That's totally fine with me. All right, so I'll give you a chance to do this, and then I'll go through them. Okay, so we have NO2. Remember, we do not say if it has just one element in the prefix, we do not say mono. So that would be nitrogen monoxide. Nope, sorry, there are two. Nitrogen dioxide. And so that's what we would do, di. We have diphosphorus trioxide. Carbon tetrabromide. AS is astatine. No, arsenic. Arsenic. Pentachloride. Sulfur. Hexafluoride. All right. Heptacarbon. Octahydride. Now, I'll explain after this. So, nonacarbon. Decafluoride. Now, these are organic molecules. Well, I guess this one isn't because it doesn't have a bond from carbon to hydrogen, but this one is an organic molecule, C7H8. And so it actually has its own own type of nomenclature, but like it has its own type of naming scheme. I'm not going to get into it though. But heptacarbon octahydride is just fine with me. Okay. And so there are some that have different systematic names. So hydrogen sulfide, H2O, we call it water, and ammonia, we call it ammonia. Also NH4 plus, we call that ammonium. Now, there's not too many, so you should probably memorize them, but if you don't get to, then I will also accept the other names for it. Okay, so hydrate. This is what we dealt with previously, but hydrates are things with water molecules attached to them. And so we are going to use the same Greek prefixes to name these hydrates that we did before. So nickel 2 cyanide. Cyanide it's a polyatomic ion with a charge of -1. There's two of them. But we don't, for polyatomic ions, we don't say dicyanide or anything like that. We don't say tri. We just, and this is also not, this is a molecular, this is not a molecular compound. This is an ionic compound. So we do not say di or mono or tri or anything like that for ionic compounds. And so we say nickel 2 cyanide. There's two negative charges. We'll multiply that by 2. We get nickel 2 cyanide. And then since there's one hydrogen, we say monohydrate. Nickel 2 cyanide monohydrate. Okay. And so if there is no water present, we can call that anhydrous. That means there's no water on there. And so we will not be discussing we will be discussing that, but you just say basically what it is in an ionic way. You do not say, you don't say what, how many hydrates there are. Okay, I think we left off here, but let's go through and name these, and then, yes, the chemical reactions I've already made a video for, so I won't be going for that, but let's go through and name these. So, if you want to give it a shot, go ahead and do that by yourself, and then I will explain what each of them are. So what's cool about these is that they will change color depending on whether they're hydrated or not. And so let's go through it. We have COCl2. Cl is a halogen, so a halide, so it's going to have a negative charge, so we would call this copper 2, because each of these is going to have one negative charge times 2, which means copper has to have a plus 2, chloride. And so this is the exact same thing, there are just 6 waters, so we would say the same thing. Copper 2, chloride, De hexahydrate. CuSO4. SO4 is a polyatomic ion that is common, and this is sulfate, so it has a -2 charge. It's also one of the ones that will have the same charge as the root element, so that is going to be sulfur, which has a -2 charge, so that's going to be copper 2 sulfate. And this is going to be the exact same thing over here, and so we'll just duplicate it so I don't have to write all that out again. And this will be copper 2 sulfate penta, because there's 5, penta hydrate. Okay, all right, that's where I'm going to leave it for week 2. Thank you so much for, if you stayed all the way. I don't know, put something in the comments. Let's see how much engagement I can get. Oh my god, maybe I should be a YouTuber. Okay, bye.